Amnon.
So the title is a bit presumptuous. Now, given the gap between our engineering successes and the wide spectrum of human perception abilities, the gap is staggering. So the title itself doesn't have any meaning. It's not well defined unless we narrow the domain. And this is the secondary title that I'm going to talk about, the domain of making the car see. And I'll be modest. I'll be talking about technologies that I think can be implemented within 5 years, say 5 to 10 years. And where this field of making cars see has the potential to reach within 5 years, and what are those technologies that we'll need to develop. So just a slide of a recap. Today's technologies center around a camera looking forward, front-facing, doing about 5 different functionalities, lane departure warning or lane analysis, detecting cars and performing forward collision warning and braking on cars, detecting pedestrians and doing the same thing on pedestrians, detecting and reading traffic signs, about 60 to 80 different traffic signs, and also doing certain lighting functions. At night, be able to automatically determine whether the high beams should be on or off. And where this is going is towards autonomous driving within the next 5 years. In terms of the computer vision technologies, the 3 main areas are object detection, cars, people, traffic signs. There's a lot of motion estimation going on, both understanding the motion of the host car, how the car is moving, and understanding what other cars are doing, kind of a friend and foe determination, and roadway understanding, which is like a light scene understanding. So the next slide, there are these clips that are running in a loop, so you can look at them in a relaxed mode. So the one on the top is detecting cars and pedestrians. What you see here is detecting lanes and road shoulders and all what is necessary in road analysis. Here you see some motion understanding. Whenever there is a lateral motion, it is colored, the dots are colored in red, and all the static points are colored in green. So there is a necessary ingredient here is to detect the ego motion, the motion of the car, in order to know what is moving and what is not moving. And here is the friend or foe estimation. The red rectangle is the car in a collision course, in a possible collision course, and the white color is the cars in the neighboring lanes. The system needs to know how many lanes are in the field of view and what the cars are doing, the average speed of cars, whether there is an escape lane in case of an accident, and so forth. In terms of what remains hard to do in this context, one is the scalability of object recognition. Engineering success is really limited to a small number of object classes. It means if the task is given an object class, go and detect it reliably in the image, this is possible. If the task is you have 1,000 object classes, go and find instances of these object classes in the image reliably, this is still an open problem. And the second hard thing is the situation awareness of scene understanding in the context of automotive. Is what is happening in the scene. It's not only where are the objects, but what the objects are doing with relation to one another. So in terms of scalability, as I said, we can conjecture, given the engineering successes that we have seen so far, that O of 1 classes can be done today. Now, this is a controversial conjecture, but bear with me and let's agree that this is possible. And if we assume a linear scalability, that means if we need X computational resources for one object class, then we will need 2X resources for 2 object classes. This linear scalability will not work when we have thousands of object classes. And thousands of object classes is what human perception is all about. Now, we effortlessly can find instances of thousands of object classes. So the linear scalability means that we'll need to replicate resources, and this is definitely not something that is workable even in the context of very large computing power. In terms of in the automotive space, the areas in which you find a need for multiple objects. In traffic signs, you have there a sample of the different kind of traffic signs. In addition, there'll be stop signs, yield signs, traffic lights to be detected. There's guardrail, concrete barriers, road edge poles, bridges, and then the list goes on. And there's about 100 different object classes that are being identified today. And if you want to go into autonomous driving, it's at least 1,000 different object classes that you need to know where they are in the image in order to properly do semi-autonomous driving. The clip that you are seeing is the system detecting all relevant objects and also understanding what those objects are. This is an example of a clip where it's a challenge for any computer vision system. So you have a camera moving in space, both outdoor and indoor, and any object that it sees in its path, there is a label of what that object is, or whether it's an obstacle without a label. This is something that I'm gearing towards, the ability to store thousands of object classes and find them effortlessly in real time on a portable system. This is something that I think can be done within the next 5 years. In terms of situational awareness, what are those scene understanding elements that are needed is, for example, find the lane boundaries when there are no lanes. Simply knowing what other cars are doing, where other cars are moving. The position of static objects like parked cars also gives you a clue. What are the boundaries? What are the lane boundaries, even if there are no painted lanes? Travel planning, how many lanes, traffic dynamics in neighboring lanes, whether there is an escape lane or not. Where are the objects of interest located? For example, is the pedestrian located on the road? Is the pedestrian located on the sidewalk? Where's the face or the posture of the pedestrian located? Is it located toward the collision course? Is it located in another direction? What do the pedestrians do? What do other cars do? This is also something that is necessary to understand when you go into autonomous driving. In terms of new research directions, again, I'm limiting it to this particular space. So one of them is scalability. As I mentioned, the linear scalability is not workable. One needs to develop a principled way of reaching sublinear logarithmic growth of resources as a function of the number of classes, which means that when you go and do classification, it's not a one versus all classification, which is the popular way of dealing with multi-class today, but it's subset of classes versus subset of classes. And the challenge here is that if you have n classes, there are 2 to the n subsets. So the question is, how do you, in a principled way, avoid this curse of combinatorics and do something that is theoretically understood and works? It's not that there's no research in this direction. Here at MIT, there's a nice paper by Bill Freeman and Antonio Torrabla, but it's a drop in the water. It's a drop in the ocean. This is an area that is understudied and needs to be pushed forward significantly in order to make room for the issue of scalability. Processing video, by and large, our community is single frame centric. If you look at all our data sets for machine learning and computer vision, they're all single frame. In the work that we've been doing in Mobileye, the fact that you process video is critical. All the engineering success comes from the fact that you are not looking at a single frame, but looking at video. I have here a second. No, I don't have. So I wanted to tell a story, but I'll put that aside. Microprocessors. Most people are not aware of the fact that the hardware that you have is will also determine the kinds of algorithms that you can run. Most applications in vision require a portable system. It's not that you'll be running the algorithm on the cloud like Google can do, but it has to be done on a microprocessor, low power consumption because it is portable. And